Hello and welcome to Talk Julia. My name is David Amos.
My name is Randy Davila.
So, Randy, before we hopped on the call today, I tweeted from the Talk Julia Twitter account, which is at Talk Julia Pod, to ask people to tell us what they're building with Julia language this week or what they've been doing. And we got some really interesting responses. There's some cool stuff out there. For example, Elias Carvalho is contributing to the development of table transforms.jl, which is for making transforms and pipelines with tabular data, which is pretty awesome. But there were a couple of interesting projects, one in particular that I wanted to point out. This one from Clemens Brunner, heartbeats.jl. So I took a quick peek at it, and it looks like a machine learning algorithm to detect heartbeats out of ECG data, which is pretty awesome. And he's got all of his code here that you can take a look at. But what was really interesting to me was that this code is from the Sleep ECG Python implementation, which he also wrote. But he mentions it's about 18 times faster than Python and only about 2 times slower than C. So that's really awesome. And he's got some benchmarks here that you can see how he did that. Really great stuff. Thanks for sharing. Thanks everyone for sharing what you've been working on. But there's something I noticed about most of the responses that we got. Almost all of them are science related. One person was doing something with chemistry, I think. Supervised learning model to predict BDEs. I had to look that up. I looked at her profile, and she's in computational chemistry. So I think it's bond dissociation energy, predicting that and molecules and stuff. But a lot of science and mathy type stuff going on, and that's kind of the background we come from as well. Maybe you more so than myself. Recently, I've been doing a lot of other kinds of programming. I know you wanted to talk about something that's near and dear to our hearts, and that is graph theory and using the Graphs.jl package.
Yes. So I don't think we've mentioned this before in the podcast, but David and myself, we sort of became friends as undergrads because of graph theory. Or not because of it, but that was a big part of why we became the friends that we are today.
Yeah.
In particular, we had an advisor, Dr. Pepper, who was a graph theorist, and David and I were really energetic young mathematicians. And graph theory is really easy to kind of jump in and start asking questions and pestering professors for answers, trying to figure out answers on our own. And David and I even have two publications together.
I think we have 3 actually. Yeah,
there's 3. Okay, so for those of you that don't know what a graph is a discrete mathematical object that is descriptive of relational things. Right? So anytime you can define a relation, like a binary relation between objects, anytime you can do that, you can define a graph on that object.
Yeah.
For example, on the Graphs.jl homepage, there's several packages to interact with graphs. But just to get started, if you wanted to maybe examine a built-in graph like a path. So a path graph is a sequence of vertices and edges. There's no loops. It's kind of one of the simplest families of graphs that you start with when you learn about graph theory. If you type using graphs, and then I'm going to also look at using graphs plot or graphplot.jl. The graphs package has these path graphs built in. So in front of me, I have a path graph on 6 vertices. And then if I want to know the number of nodes, I would type NV, which number of vertices. So one thing that I immediately noticed when looking at this whole suite of packages on graphs is that they use vertices instead of nodes.
Yeah.
And as a graph theorist, my PhD is in graph theory, I tend to like that more. And the reason why I would type nodes automatically when working with programming, or say nodes when programming with graphs, is because I come from using a package called NetworkX in Python. Yeah. And NetworkX in Python is kind of the standard package for doing graph and network analysis in Python. And they like to use nodes. But I immediately noticed that with all of these Julia packages, though, for graphs, so graphs, light graphs, graph plot, all of these packages, they prefer nodes, which is kind of nice. So if I want to maybe look at the number of edges, it's really simple. It's very natural just to call a function NE. Also, the graphplot.jl package, I really like how the graphs are formatted out of the box. So graphplot has a function called gplot, and it will plot the graph that you've instantiated. And by default, this Springer layout, which is kind of the default layout in NetworkX as well. This is a great package and has all of the functionality that you would possibly want. So for example, a lot of times people are interested in distance on graphs, not like Euclidean distance, but if you start at one vertex and you want to traverse to another vertex, what's the shortest number of edges that you need to pass through to reach the other vertex? So that'd be like the distance between two vertices.
Yeah.
Right. And this is also important with weighted graphs. When graphs have weights on the edges, which there is a simple weighted Graphs.jl package that you can use for this, where then you might want to be concerned with like a famous problem is like the minimum spanning tree problem.
Right.
Like finding a spanning tree, which is a subgraph that has no cycles and contains all the vertices in the supergraph and has minimum weight if you sum all the weights on the edges. But yeah, so like all of these things, there's algorithms built in to Graphs.jl. So like cycle detection, here's MST, the minimum spanning tree problem. They have graph coloring, which is one of the most well-known graph theory problems where you want to color vertices so that no two vertices that share an edge have the same color. This is related to this famous four-color theorem for maps. Linear algebra, lots of linear algebra functions and properties here. And the reason for that is that graphs and linear algebra are highly related. So you can represent a graph as a matrix, and you can also represent a matrix as a graph. This is a relationship that is probably the strongest among like the computational fields and the graph theory fields, is this tie between linear algebra and graph theory. David, tell them about Grinpy, and then I'll mention why I wanted us to talk about that in a second.
Okay. So Randy and I started developing, I don't know how long ago it was now. It's been several years, a Python package. It basically builds off of Network X that we use to calculate things called graph invariance. So if you have a graph, you can move the edges, move the vertices around and sort of draw it in many different ways and different shapes and everything. But there's properties of the graph that don't change no matter how you draw it. So those are these variants. And a lot of them are really difficult to calculate, but you'd wish, if you're doing research, you'd want ways to be able to quickly calculate them.
A lot of these things are NP hard to compute, or NP complete decision problems. And something that we noticed were not available on Network X, and then also not available on Graphs.jl currently.
Yeah, there wasn't really anything that we found out there that would calculate a lot of these things that we were interested in for our research and stuff. So we made this Python package that does a lot of these, calculates invariants, and it's seen some use by other, folks, other academics, and still kind of get emails occasionally from people that find it and have a question about something. But honestly, after working with Julia for, I guess I've been doing it for a little month or so now, a little over a month. I would really like to go back and redo a lot of that stuff in Julia and either contribute to the Graphs.jl package or do something outside of it that works with it, something like that. But I know, Randy, you've actually done a lot of work already taking some of those algorithms.
Yeah, that's exactly what we're getting to. So one of the main reasons why David and I created Grinpy for calculating these invariants was to make something called an automated conjecturing program, which this is a program I wrote in Python called TX Graffiti. An automated conjecturing program automatically generates new mathematical questions for researchers to work on. I started looking into making a Grinpy version type of program in Julia with Graphs.jl, but I needed an optimization solver like Pulp was in Python. And I found something that's pretty awesome, and I think a lot of people are very familiar with that are listening, called JuMP. JuMP is the coolest package for performing mathematical optimization in Julia, and supports a bunch of different types of commercial solvers and open source solvers for solving problems like linear programming, mixed integer programming, semi-definite programming, and even nonlinear programming. And the interface for it is awesome. I love showing students how to use JuMP to write linear programs for solving mixture problems or basic things you would find in operations research, right? I teach operations research every once in a while, and I use JuMP and Julia for these simple problems because it's so easy for the students to pick up, in that the way that you set up problems looks exactly like the textbook. So for example, look at this simple program in front of me. You have a model where you're instantiating an empty model, but then you call these @variable macros to add variables. So you're adding to the model some variables, say 3 of them. And then in that same at variable macro, you have bin, right?
For
So that's like the type
binary.
of, yeah, exactly. So binary objects. And then you have constraints, and you can just list out the constraints as they would appear in a textbook, honestly. It's
Yeah,
like x1
it's
is
really
less than or
nice.
equal to x3, x2 is less than or equal to x3, x3 is less than or equal to x1 plus x2. It's really cool. And I haven't like written these like graph theory optimization problems in Julia since like 2019, but I have a whole list of them somewhere on my desktop. I have almost every single thing that we did in Grinpy, I have in Julia with JuMP and Graphs.jl.
Nice.
So it's like the Julia version exactly of what it like Pulp and Network X.
I want to go back real quick to, you were talking about the linear algebra module in Graphs.jl.
Yeah.
So I have been interested in sort of the interplay between graph theory and linear algebra for a really long time. It started when we were undergraduates. And one of the things that I did when I was an undergraduate for my senior project was work on a problem that was related to spectral theory, where not to get into all the gory details for the non-mathematicians out there, but basically, if you have a square matrix, then there's these values called eigenvalues that get associated with it through the characteristic polynomial. So these things you can calculate on graphs and everything. And these eigenvalues have, well, they're really important from a linear algebra standpoint, but they have other applications, not only in graph theory, but also in applied graph theory. And the particular arrangement of these eigenvalues, which, if I remember right, it's the absolute value of the product of all the eigenvalues. Maybe it was the sum. I can't remember now, but it was called the graph energy, and it was related to chemical energy because the graphs are used a lot in modeling like molecules and things in chemistry. And this notion of graph energy was related to like the chemical energy of a molecule. But I came across a long time ago an idea. I came across it on Randy, you'll know who this is, Fan Chung, her website. But it was this idea of taking graphs and turning them into music. And so having my background in music as well immediately piqued my interest. I looked at it and kind of filed it away in the back of my brain for a long time. But it recently surfaced again, and I dug some more into it and ended up writing a Julia program to mimic what this was doing to create these musical chords. And it was a really nice experience. But just to, I guess, kind of set the stage, if you imagine a cycle on 4 vertices, right? So you have 4 dots and you connect them in a cycle with lines. So it looks like a square or rectangle. Then the eigenvalues, you have a 0 eigenvalue, one of those, you have eigenvalue of 1, which has multiplicity 2. That's like algebraic multiplicity in the characteristic polynomial. And then you have 1 eigenvalue of 2. You can convert these to frequencies. So I guess I should clarify, I'm talking about all this stuff. What matrix is this coming from, right? So you take the graph and you calculate its normalized Laplacian matrix. So it's a matrix that you can calculate from the graph itself. You calculate its eigenvalues and you get these values. The normalized Laplacian matrix has some nice properties that guarantee that those eigenvalues are always going to be in the interval from 0 to 2. So it gives you kind of this closed interval that you can map to different things. And one of the ideas is, why don't we take that and map it to frequencies that we can listen to? So you take 0, and which is the smallest eigenvalue you can have, and you map that to the note A at 440 hertz. And then you do the same thing at 2, or sorry, at 1, the value of 1, you map that to A 1 octave higher. So that's 880 hertz. And then you take 2 and you map it to another octave higher than that. That is 1,760 hertz. So the actual formula to do this is it's just 2 to the x times 440 hertz. So you can take that and you can you get the different tones for each eigenvalue. And if you have a multiplicity of greater than 1, like if you have 2 eigenvalue, well, technically it would be 2 eigenvectors with the same eigenvalue. Lots of math stuff, right? Sorry to get super nerdy on it, but if you have those, then basically you just double the amplitude of that note. It just increases how loud it is in the resulting like notes that you get, and then you can play them all together in a chord, and you get a chord out of the graph. What is absolutely mind-blowing to me is that it's not just noise, which to me was just like kind of shocking. Like, why was it not just noise? So yeah, I was just kind of blown away that that they actually sound as nice as they do. And maybe I'll play some. Well, I'll play one right now. Interesting tones. So I was like, okay, I want to recreate this, and I started to build it out in Julia. It's just a little script. And what was interesting, so I had to use the Graphs.jl package, and I had to calculate the normalized Laplacian matrix, right? And it has a a composite type called normalized Laplacian, but I couldn't figure out how to use it. The docs didn't quite get me there. Fortunately, I found an issue, GitHub issue on their GitHub repository where someone else was trying to do the exact same thing, and I read through it and found a solution that looks exactly like the one that I have in my program. I'll put a link to this if anyone is interested in actually seeing it. But I got to use a lot of cool stuff, right? Like I got to use some of like the Unicode support and put like the little hat on top of the A for like the normalized adjacency matrix, and on top of the L for the normalized Laplacian. I learned about using the sparse arrays package, which was really nice. And then also just the base linear algebra package in Julia, right? To get a matrix and actually compute its
Oh,
eigenvalues.
it's so awesome. I love it.
Yeah,
I
yeah.
love that it's based Julia.
I know it's great to just have that in there. Not you don't have to install anything else or and anything like that. So yeah, it was a lot of fun, and I also got to play around with plotting the graphs. So I have a couple of actually scripts that I wrote. One of them just creates these, creates the tones and makes the chord or the scale, which would just be like playing the tones in order, not stacked on top of each other. And to do that, I used this wave package, WAV, right, for making wave files, which made it really, really easy to just.
Was that a part of that music suite, like the?
No, it wasn't. It's a separate deal. But I thought about playing around with that, even that we talked about a couple of episodes ago, to maybe try to actually produce like the musical notation. So you would like feed it a graph object, and it would give you like an image that has like the musical notation for that graphs chord. Kind of neat. But yeah, the wave package made it really easy to just create wave files. And then I also plotted these. I used the graph recipes package. Have you seen that, Randy?
Yeah, I've seen that one.
But anyway, it was a lot of fun, and I really got to try a lot of the things I've been learning about Julia in this, and I'm really, really happy with how it all came out looking, how it worked.
Now we should probably like let the listeners know that this is your first real experience programming in Julia. Like, yeah, you've programmed in Julia, but this is the first time you had like a task that you really wanted to do, and you used Julia as the only language to do it.
Yeah, I'd done little experiments, and like I'd made like a little like number guessing game, and like just practicing with like you making a module and learning how to do that, and little things like that. But yeah, this was the first time I really sat down and said, okay, here's this thing I want to build, and I'm going to build it in Julia. And it was a really fantastic experience. I learned a lot, but I think the biggest takeaway for me was that Julia is a real dream to work with the whole way through, from working with the package manager and installing the packages to running it, writing the code, and everything. It was nice.
Well, listeners have access to this script that you wrote.
Yeah, it's publicly available. I'll post the link with the show notes so that people can see it.
Awesome. I think that I'll make like a little sample repository to demonstrate how to use Graphs.jl and JuMP to calculate the independence number of a graph. I'll make like a little repository, and I'll have that available for our listeners to go check out, so they can like see the things that we're starting to code more and more in Julia. So if our listeners want to see it, like I don't have a problem putting my code somewhere for them to look at it.
Awesome. Yeah. Well, one of the things that I kind of ran into when I was doing this project was I had read some articles and in the docs and stuff that, okay, I want to create a new environment, right? Like I want to create a project environment for this that has the dependencies that it needs. I don't want to put it in like my global Julia environment. So I used the package manager to activate a new environment, and I installed the stuff in there. I wrote my script, and the first time I went to run it, I typed Julia, and then whatever the script name was, I think I called it like graph music. I typed Julia graphmusic.jl, hit enter, And the first thing I saw was a module error that it couldn't find the Graphs.jl module. And I'm like, okay, that seems really weird, right? Like I installed it. Then I thought it's probably not using my project environment. Like the Julia command is probably not aware of this project environment. It's just using my base Julia environment, like my global environment there. So I looked into it, and sure enough, that's exactly what was going on. It was like, okay, well then how do I tell it to use this project environment? And there's a command line options reference in the manual. I saw, okay, there's this -- project option, and you can actually you can give it like a path to wherever the project files are, like your project.toml and your manifest file. Or there's a default option of this @ which will just it'll look in the current directory or go up, it'll walk up the parent directories to see where it finds the project files.
So like the toml file. Oh yeah, I didn't even yeah, it'll find the toml file.
So if you want to run run a script and use whatever the project environment that you're in right now is, you would type Julia -- project and then the name of the script that you want to run. I thought, so I guess I had two thoughts about that. One, like on the one hand, it's like, okay, I actually kind of like that I have to explicitly tell this thing what project to use, because I like explicitness. It's just, I know exactly what's happening. There's not like something invisible that's going on. But on the other hand, that's a lot to type if I'm like running it a lot, right? So I thought there's got to be like a shorter way or something. And I found in the environment variables part of the documentation, there is an environment variable called Julia project that you can set. And if you set this to that @value, then by default, when you type Julia to use the Julia command, it'll search for like an existing project wherever you are, or like up the directory tree, up the parents. So you can give it that sort of default behavior of not always, defaulting to the global environment, but use, whatever environment for my project. But I want to say that I actually decided not to do that. I thought, okay, that's pretty cool. I'll just set that, and have that, always set to that default, or not to the default, but always set to that @ and make that my Julia command's default behavior. But then I thought, actually, I don't want to do that, because then I'm going to get used to it on my machine. And if I go anywhere else and I'm using it, I'm probably going to forget, and it's,
Yeah,
and it's not going to work that way. And it's like, well, I like being explicit. I like saying that I want to use that project. So what I ended up doing is I opened up my bash.bash rc file, where you can set your environment variables or create aliases for commands or things like that. I actually added an alias to it, which is Julia P. So this creates a Julia P command that it just is short form for Julia --
yeah, and just initialize the project.
So I just do not initialize a project, but like if I want to run the file, run my script using the current project, I just type Julia P space, myscript.jl, as opposed to Julia myscript.jl. And that way I still have both commands, right? Like I still have a Julia command that is always going to use the global environment. And then I have this Julia P that will like search for the project environment. So just a little, I guess, tip I wanted to throw out there, and, things that I learned and experienced while I was doing my first end-to-end Julia project.
I have to admit though that note that I've suggested altering the bash file before for students, and had some pretty horrible results from it, just because they'll get rid of things and not remember what they got rid of, and then running conda or something else just won't work anymore. So be careful.
yeah your dot files, like your bash rc, all these dot files and stuff, you want to be careful with those, but they're also a really powerful tool, to make sure you use them. So, but I don't know if you have any closing thoughts on anything. So I guess real quick, so what do we say? You're going to create a little GitHub repo that people can look at with a example of using JuMP to calculate the independence number.
Yeah. And I don't know if it'll be up by by the time that the podcast posts, but a link should be given so that over the coming weeks, you'll see code start to appear. Basically, I think I'm just going to start putting together all these integer programs to calculate the graph invariance that we might make into a package one day.
Yeah, awesome. Yeah, that'd be another really fun experience, actually putting together a package that we can register and learning that whole process. One thing that I'm really curious, I've read a little bit about, and I've done like very minimal in real life, like just some real small examples, but into testing with Julia, like how do you actually run tests and everything. There's like this @test macro and stuff that you can use. And anyway, so that's something I'm kind of excited to dig deeper into and learning about, just the whole packaging process and getting it registered.
This year I'll probably make a automated graph conjecture program in Julia.
That'd be awesome.
Because I have all the data. I have like hundreds of thousands of instances of graphs.
Right.
And as soon as I know how to calculate the data on them, the process of writing an AI program to automatically sort through possible questions to ask and sift them, I think Julia would be really fast at doing that. And it would give me motivation to work on it again. I haven't worked on this conjecturing program in a while. I wrote this program while working on my PhD. Like I didn't, it appears in my dissertation at the very last page. Many of these problems were, but I spent hours and hours and weeks and months working on this program. But once I got the initial versions of the program running, it started producing conjectures that happened to be new and interesting, which my advisor and I worked on. And I think by the time I finished my PhD, I had 18, 17 publications in like discrete math, discrete applied math. Wow. Because of that program, because it was just spitting out so many different problems. That was a tangent, but I want to do that in Julia.
All right, man. Well, thanks again for hanging out and talking about Julia with me this week.
Awesome. And I guess we'll pick back up next week.
Sounds good. See y'all then.